Welcome to This Explainer. Today, we are literally cutting right through all those layers of abstraction we're so used to in modern technology. We're going to strip computing completely down from the high-level software you interact with every day, right down to its physical 8-bit electronic foundation. We really want to see exactly how pure hardware logic operates.
Because, when we actually deconstruct our devices, we inevitably reach the absolute baseline of all computing. It makes you wonder, what exactly is the fundamental atom of a digital circuit?
Well, that atom is the transistor, and by extension, the logic gate. These microscopic foundations are the absolute bedrock that make every single digital action and literally every layer of software abstraction physically possible.
So, here is our blueprint for today's explainer. We're going to start by stripping down modern tech. Then we'll look at the atoms of computing, dive into the hardware's steady heartbeat, and finally wrap up with the 4-stage execution cycle.
All right, let's jump straight into part 1, stripping down modern tech to look inside the black box.
Modern processors kind of feel like these microscopic black boxes, right? Billions of actions are just happening invisibly, completely hidden beneath layers of abstraction. But by constructing an 8-bit foundation on a physical breadboard, we drag all those hidden processes right out into the open. It makes the complex visible and, honestly, strictly mechanical.
Ben Eater's incredibly popular educational project illustrates this perfectly. He actually builds a programmable 8-bit computer totally from scratch using standard physical breadboards. The whole thing relies strictly on basic components like transistors, logic gates, a clock module, and RAM. It just proves that a computer is essentially a highly organized, hand-wired machine.
Which brings us to part 2, the atoms of computing. Let's talk transistors and gates.
So, transistors act as your raw electronic switches. But when you wire them together into logic gates, they actually elevate physical voltage into binary logic. These gates channel electricity to perform Boolean operations, serving as the essential building blocks that physically process information before any software is even involved.
Okay, moving on to part 3, the hardware's steady heartbeat, specifically the clock module. Because here's the thing, when you wire thousands of logic gates together, you immediately run into a massive engineering hurdle: timing. So what exactly does a clock module do to prevent the whole system from just collapsing in on itself?
It synchronizes the steps of the CPU to maintain a steady operational rhythm. Without hardware synchronization, tiny variations in propagation delay across different logic gates would cause data collisions and instantly crash the whole shebang. The clock module acts like a conductor in an orchestra, ensuring that every state change across the architecture steps forward at the exact same time.
And that leads us to our final section, part 4, the 4-stage execution cycle.
Every single command flows through this physical 4-stage cycle. First is fetch, which grabs the instruction from memory. Then decode, which passes it through those logic gates to physically route the command. Next is execute, performing the actual operation inside the ALU. And finally, store, which writes the result to a register. Fetch, decode, execute, store. It is a relentless physical loop driven entirely by the clock's pulse.
This really brings us to a perfect summary from our source material. It, quote, provides a foundational overview of computer engineering by stripping modern technology down to its essential electronic building blocks. Projects like this prove for sure that computing isn't magic. It's just an incredibly clever orchestration of physical hardware. It takes something esoteric and makes it entirely tangible.
To wrap up this explainer, I want you to consider this. We just looked at a relatively simple 8-bit architecture that you can literally build by hand on your desk. But knowing how this fetch, decode, execute, store cycle works at the purely physical level, how many billions of these tiny synchronized atoms do you think are beating inside the massively powerful processor you're using to experience this explainer right now? Thanks so much for joining me on this dive into hardware architecture, and I'll see you next time.